Hello, we are very delighted to have Shu-Heng Shao. He will talk on lattice axial symmetries.
Hi, thank you so much for having me. So I'll talk about a recent paper I wrote with really two excellent MIT students, Arko Chatterjee and Xiao Pace. The archive number for the paper is here. Okay, so let me jump right into it. Oh, and it's so please feel free to interrupt me anytime. I cannot see most of you guys, so it would be nice to have more questions so that I know if I where I am in the talk. Okay, so the general question I want to ask is that given a QFT, given a continuum quantum field theory, can we realize its chiral symmetries and possibly their anomaly, if there's any, on the lattice? Okay, it's a very old question, and I think to this audience, I don't necessarily have to give the motivation for this question. Among other things, we would like to put the standard model on the computer, and the gauge group in the standard model is chiral. So you would like to realize the fermions in some way so that the chiral symmetry is there on the lattice. But on the other hand, this is also known to be a difficult question for various reasons, and I will review a couple of them. So today we will address this question from a slightly different angle, and I'll focus on the simplest setup possible and try to offer some new insight. So what's the simplest setup for this question? Simplest setup. The simplest setup would be, so what's the starting point quantum field theory I want to talk about? The simplest one will be a free, massless Dirac fermion. Oops. In 1+1 dimension. Okay, cannot get simpler than that. And let me just quickly remind you, actually, usually I wrote the gamma matrices, write the Dirac action in terms of the gamma matrices. But since I think this is a string theory audience, I can use the Marana-Bio notation. So a Dirac fermion in 1+1D is made out of, let me write it here. It's made out of a complex single component biofermion, a left-handed biofermion plus a right-handed biofermion. Okay, and the Lagrangian is simply I psi left dagger, the one we usually use in string theory. Okay, so far so good. So this is the continuum theory, and what's the symmetry we are shooting for? Well, this model has an O2 times O2 symmetry, but I'm going to focus on two U1 symmetries. The first one is a vector U1, which just rotates the left-handed fermions and the right-handed fermions by the same phase. And the axial one rotates the left-handed fermions and the right-handed fermion by the opposite phase. Okay, so the key point is that here is plus. All right, so the goal is whether or not we can realize both the U1 vector and the U1 axial on the lattice. A very quick comment is that the global form of the group is not U1V times U1A, but it's U1V times U1A with their Z2 subgroup being identified. You can readily see that they share the same D2 subgroup. But that's not terribly important for what I'm going to say. Any question up to this point?
Yeah, Shu-Heng. So two questions.
Yeah.
One, just to make sure. So as a CFT, this would have C equals C tilde equals 1, right?
Correct. Yeah. So C left, because I have 1, so C left is 1, C right is 1.
Yeah. And the other sort of basic question I had was, so you want to get a lattice model where U1V and U1V are both exist in the action on the lattice degrees of freedom, right? Like they should.
Exactly.
Okay.
Yeah. Exactly.
Okay.
So I'll get to the lattice model in a few minutes.
And this Z2, sorry, and also the Z2 is when the theta is just pi, right? Both coming up the same sign.
Exactly. And you see that if you set theta to be pi, then the actions of vector and axial are the same. They just flip over by a minus sign.
Mm-hmm.
Right. Good. Okay. Doing on time. Okay, this clock here. Okay. Okay. I think since it's a Zoom talk, I might be able to cover even more materials. So, well, what's the anomaly of this model? There are two ways to view it. So let me present both perspectives, because I think the word anomaly is the single most abused term in theoretical physics. So it's nice to get it straight what we mean by anomaly. The first notion of anomaly is that you can gauge the U1 vectors. Well, if you gauge the U1 vector symmetry, this model has a name. It's QED, U1 plus 1D. Let me just do I want to be explicit? No, I don't want to be that. Well, let me be explicit. So in terms of the gamma matrices, I can write a coupling like this. So now psi is psi left, psi right. So it's a two-component Dirac fermion here. And then there's a Maxwell term. But we're in 1 plus 1D. So the electric field, the only field strength is the electric field. And it's EX. So I'm not even going to bother to write the X subscript. E is just DTAX minus DXAT. So I think the first person to study this model was Stringer in the late 50s, early 60s. And famously, this model has a Stringer anomaly. Now, what's the statement of the Stringer anomaly? So we have two symmetry, U1V and U1A. In fact, let me move it a little bit down here. Now, these are ordinary U1 global symmetry. So there's a Noether current associated with each of the two U1s. So it's just some simple fermion bilinears. Let me now write down the explicit expression. The statement of the Stringer anomaly is that the moment you gauge the vector symmetry, then the axial symmetry is no longer conserved. So this is the statement that D mu J mu A is not 0. Rather, it's 1 over pi times the electric field. So many people refer to this anomaly. Well, so this is the statement of this anomaly is that classically the Lagrangian has an axial symmetry, but quantum mechanically is broken. So the upshot is that classical symmetry fails to be a symmetry quantum mechanically. Many people attribute this anomaly to Stringer, but when you actually read into Stringer's paper, I had a hard time finding where Stringer actually said it. I think there's another paper that who stated this more clearly, which was by Ken Johnson. at MIT in 1963. Okay. Now, so this is the anomaly in the Schringer model, but you can ask, can you already see this anomaly in the original Dirac-Fermion model? Or what's the fingerprint of this equation in the free Dirac-Fermion model? By the way, this anomaly just comes from the simple one-loop Feynman diagram. You have JA here, JB here. This is really the simplest anomaly possible. I think probably many people first learned the ABJ anomaly in 4D, and that will correspond to a triangle diagram. But this is the even simpler version of that in 2D, where it's just a two-point function. Now, there's also a fingerprint of this anomaly in the free Dirac fermion. In the modern terminology, we will call it the 't Hoof anomaly. In the Dirac fermion theory, I'm going to make this 't Hoof adjective very, very small because all this development happened before 't Hoof's anomaly paper. So what's the statement there? The statement in the free Dirac fermion theory is simply that you cannot gauge U1V and U1A at the same time. And indeed, you see that if you gauge U1V, you go to QED, and then U1A just disappears. So these are not unrelated facts. And the way to diagnose or describe this anomaly was famously pointed out by Schringer in 1959 in the same paper here, where he found that the equal time commutator between the vector and axial symmetry current doesn't vanish, rather it becomes a derivative of the delta function. And this is famously known as the Schringer term. Okay. All right. Any question up to this point? I think so far I have been only reviewing physics in the 60s or 50s.
So isn't there a similar commutator between like J0 and JX or something, J0 and J1?
Very
What's
good.
that state?
Right. So JTA turns out to be proportional to JXB.
Oh, okay.
Yeah. Because it's just because J mu V is roughly epsilon mu nu J nu A. Yeah. So indeed, if you look at Schringer's paper, he phrased everything in terms of JB. That's the reason why I said I feel like the anomaly was not really pointed out in Schringer's paper. But if you look at Ken Johnson's paper, he relates the vector currents to the axial current. Yeah. Great. All right, so now I can ask my earlier question one more time. Can this anomaly be realized on a lattice? Now, given that we are talking about fermions, typically lattice fermions, give you a finite dimensional local Hilbert space. What do I mean by that? You have a lattice. On every lattice side, you have a bunch of fermions, 2 or 4, any number of them could also be 1. And on each local Hilbert space, on each site, you're just trying to figure out the representation of the Clifford algebra. And that's typically a finite dimensional representation, right? If you have a pair of real fermions, that's a 2-dimensional Clifford algebra. So that gives you a two-dimensional Hilbert space, so on and so on. So typically, if you just work with fermions on the lattice, your local Hilbert space associated with each lattice side is finite dimensional. You can think about it as qubit. So let me add an adjective here. Can we realize this anomaly on a finite dimensional? Well, sorry, this is not precise. On a lattice, with a finite dimensional local Hilbert space. Okay. The reason this this condition is interesting is for the following few reasons. Well, first, as I said, for practical purposes, if you work with lattice fermions, typically the local Hilbert space is finite dimensional. Second, it is known that if you are willing to work with an infinite dimensional local Hilbert space on the lattice, then it is possible to realize such an anomaly. You have to work in the bosonized picture. And third, if you have finite dimensional local Hilbert space computationally, that's much less expensive than working with infinite dimensional local Hilbert space. Working with infinite dimensional local Hilbert space means that you have to do integral over the degrees of freedom locally. But if you just have qubit on every side, then you just have to sum over it. All right. Now, there's a simple argument why this cannot be true. Namely, it's impossible to realize the Schringer term literally on the lattice with a finite dimensional local Hilbert space. And the argument is very simple. You just take the trace on both sides. Trace of a commutator on a finite dimensional Hilbert space necessarily vanishes. But the right-hand side is a delta function, which has a derivative of the delta function, which has a non-zero trace. So this simple argument tells you that you cannot literally realize the Schringer term on a lattice with a finite dimensional local Hilbert space. This is similar. Yeah.
Yeah, so maybe you should finish your thought, then I'll ask the question.
Oh, yeah. So it's similar to the statement that in quantum mechanics, you cannot realize the canonical commutation relation on a finite dimensional Hilbert space. Yeah, that's the only thing.
But I think this is a little bit maybe comparing apples to oranges in some, well,
Yeah.
I don't know, but I'm just going to ask, because, we know that if I just discretize, let's say we have a particle moving in one dimension.
Yeah.
And I discretize space and I discretize the Laplacian and put an on-site potential.
Right.
In some sense, I can recover continuum quantum mechanics, right? Like if I just take I is the discrete index and there's a complex psi of I and there's a potential of I and I write down some Schrodinger equation, in some appropriate limit, it will reproduce this by this clock and shift operators, whatever. So in some sense, we can discretize not X and P, but their exponentiated versions in some sense.
Oh, you mean you're thinking about this or maybe some nth root of
There are these while operators like e to the I alpha X, e to the I beta P.
Okay.
And they have a commutation relation.
Right.
Which is basically follows from this IH bar, but those ones can be realized on a lattice.
Yeah, but if you work with the clock model, that has if you work with the rotor, that has an infinite dimensional Hilbert space. Or maybe you have in mind the ZN clock model.
Yeah, ZN, ZN, yeah.
Right, but ZN clock model, as you said, the commutation relation is something like this, where omega is the nth root of unity.
Right. And boundary takes to infinity limit and then.
Yeah, you can, yeah. So I'm saying, indeed, there could be various lattice relation for which if you take the continuum limit, becomes the Schringer term. But the statement I was making is that you cannot literally realize.
Okay, yeah, that's fine. Then it's of the same footing,
Yeah, but if you are willing to work with the rotor, which has an infinite dimensional local Hilbert space, then you can actually literally realize this relation.
Mhm.
And by literally, I mean delta prime just becomes some difference between the Kronecker delta.
Mhm. Okay, okay. So is the point going to be that you'll basically show how to construct the analogs of this capital X and capital Z operators?
Yeah, I'll say what I realized. Oh, what we did exactly. So here is just more like a motivation. For why it's
Okay.
difficult to realize the anomaly on a finite dimensional Hilbert space.
Mhm.
At the end of the day, we do not literally have such a relation, but we have something that goes to this equation in the continuum limit, much
Right.
like what you suggested.
Right. Okay.
Any other question? All right, so that's my 20 minutes introduction. So this talk, the goal is to show that we can realize both QV and QA. So QV and QA are the integer value conserved charges for the vector and axial symmetry in a Hamiltonian lattice model. Finite dimensional local Hilbert space. Before I go into the detail, let me just give you the punchline. The punchline is that this sounds too good to be true. In fact, this is almost a contradiction of the famous Nielsen-Ninomiya theorem. So we have to give up on something. And what we will give up at the end of the day is that these two charges on the lattice don't commute. But the generators for the vector and the axial symmetries exist exactly on the lattice.
Sorry, why
Okay.
is it important to have them be integer spectra?
Good. Because I will later on talk about a charge that doesn't have integer spectrum. So the goal is to realize the U1 global symmetry on the lattice. And U1 symmetry by definition have integer eigenvalues. Otherwise, I will call it R. You can ask, why is it important? I think it's important because if you have a symmetry with the integer value conserved charge, then you know how to couple it to U1 gauge field. Right. But I'll compare the two later.
Okay.
Okay. So what's the model?
But sorry, also you mentioned this Nielsen-Ninomiya theorem, so that only applies for these integer type operators?
Yes,
Oh.
basically.
Okay.
I'll get to that in just a minute, later on in the talk. Okay, so now we can finally talk about the lattice model. And it's really the simplest possible lattice model you can imagine. It's called the staggered fermion model. But it's in 1+1D, so it's much simpler than the higher dimensional version. This model, this model I think was already known maybe almost 100 years, but it was discussed in the context of lattice gauge theory, first by Banks, Koga, Susskind back in 76, and also by Lenny in 77. So what's the model? So it's a 1+1D Hamiltonian lattice model. So that means my space is discrete, but my time is continuous. So I have my space has L different sites. And on every site, I have a single component, complex fermion Cj, together with its dagger. And they obey the standard anti-commutation relation. And CJ's C and C anti-commute, C dagger and C dagger anti-commute. And I'm going to impose a periodic boundary condition. Okay. Now what's the Hamiltonian? Well, at this point, you might be wondering that if the goal is to realize the Dirac fermion in the low energy, the Dirac fermion has two components in the continuum limit. But my CJ only has one component at every site. So we seems to be off by a factor of 1/2. The reason for that will become clear. So the Hamiltonian, the simplest Hamiltonian you can think about is the nearest neighbor interaction. So CJ talk to CJ plus 1, and you want to preserve a manifest U1. So it takes this form. Okay. This Hamiltonian, I claim, flows to the Dirac fermion. Any question at this point? I can give more details, but
Yeah, maybe I just have a historical question.
yeah.
I mean, this seems like something that a solid state physics person would write down, right? There's some tight binding model.
Yeah.
Why does it have this name like staggered? What's really staggered about this, or what?
Yeah. So when I was introducing it, I said this model indeed, I think already, maybe Jordan and Bickner already talked about it. But
Yeah,
Lipschutz Matisse in 1961 also definitely also talk about this. This stagger name is indeed probably most appropriate when you go to higher D, where the action of where the Hamiltonian will involve alternating sign. But in the chirofermion literature, they still refer to this Hamiltonian as stagger fermion. And this terminology comes from this paper in Banks, Koga, and Susskind.
Okay.
Look into their paper, they call this stagger just because in a way they put different components of the fermions on different sites.
Oh, the continuum fermion.
Yeah. So for condensed matter physicists, they wouldn't care. They don't have any continuum limit in mind. But for a lattice chirofermion person, if your goal is to regularize some quantum field theory of the lattice, then the idea is that you split your fermion into two components. I have to emphasize that this plus and minus are not a left-handed and a right-handed component. So this is in a different basis. That's some technicality. Let me not go into that. And the rough idea is that you put the one component of the fermions on the even side, and the other component of the fermions on the odd side. I think for that reason, Banks, Koga, and Susskind call this the stagger fermion. Yeah.
I see.
Yeah. People ask
I
me.
mean, written in the way sort of you wrote it this like the solid state physics people would write it as there's some atom and there's some electron and some orbital on each side and they're just hopping, right?
Yeah. It's just some tight binding model.
Yeah.
Exactly. In fact, when we were writing the paper, we had a long discussion whether we should refer to this as just some tight binding model or the stagger fermion model. In the end, we decided to settle on the name stagger fermion because that's how these people call it, and our targeted audience is more high energy people.
Makes sense.
Okay, so what are the symmetries of this model on the lattice? There's a manifest vector U1. Which just rotates the fermion by phase. All right, so that's great. We want to realize two U1s, and we are halfway there. The charge for this U1 is CJ dagger CJ minus a half. Right. Now the question is, where is the axial charge in this simple model? Okay, to that end, let's go back. to the continuum story. And I want to note one very simple fact. So this is the way the vector and the axial symmetry act on the continuum fermions. Let me call the charge in the continuum by this calligraphic V. So we have a calligraphic QA, we have a calligraphic QB. Now, if you look at these two equations, you see that QA and QV are actually related by a unitary operator. It's an operator, let me call it CR, where CR perform a charge conjugation only on the right-handed file fermion. Yeah, and I hope that is clear because the only difference between the vector and the axial charge is that you flip the sign here versus here. So if you take a conjugate on the side right, you swap what you mean by vector versus axial. Okay. So in the continuum, this, and CR takes side right to side right dagger. So given that we have already realized the vector symmetry on the lattice, the only remaining question is how do you realize the right moving charge conjugation on the lattice? Okay. Now that has a well-known answer. So let's continue with the continuum discussion for a little bit. If you decompose your left-handed vial fermion into a Marana vial fermion, into two Marana vial fermions like this, you can also do it for the right-handed one. So AL, BL, AR, BR, they are all one component, real Marana vial fermions. Then you see C right, only flip the sign of a single Marana vial fermion. So the goal at this point is just to realize a symmetry on the lattice that flip the sign of a single chiral fermion. Now that has a well-known answer. And the trick is that in this complex fermion Hamiltonian, the trick is to break it into the real fermions. So let's write, now we are back on the lattice. The trick is to write Cj as Aj plus Ibj, where Aj and Bj's are both real fermions. So Aj will eventually flow to the continuum, the left-handed Marana vial and the right-handed Marana vial for A, similarly for B. And if you write the Hamiltonians in terms of Cj, in terms of A and B, you find this. So the model is decoupled. It's a sum of two decoupled Marana fermions, A and B. And we want to find a symmetry that only flip the sign of the right mover. Is that clear at this? Any question at this point?
Yeah, I think it's clear.
Okay, great. Okay, so how do we do that? You know, if you flip, there's an obvious symmetry that flip the sign of B, but that's not what we want. If you flip the sign of B, you will flip the sign in the continuum of both B left and B right, but we don't want that. So to understand how to flip the sign of only the right mover, we need to understand better how the left mover and the right mover arise from a single component real fermion on the lattice. For that purpose, it suffices to focus on the B fermion. and forget about the A fermions. So focusing on the B fermion, let's go to momentum space. So K is the momentum, and it's identified with K plus L, and beta K is the Fourier mode. And if I look at, and now the Hamiltonian for the B fermion retaining momentum space takes this form. So the energy is given by a sign function. Let me plot the sign function. Look like this. So this is the Brillouin zone ranging from minus L over 2 to L over 2. This is K equals to 0. And near here, you have the right moving fermions. Near here, you have a left moving fermion. So this is the key idea of the staggered fermion. That naively, in the continuum, the dispersion relation is just E equals K, or E equals minus K. So naively, you want to realize your fermion such that it gives you the linear dispersion relation. But that's impossible on the lattice. On the lattice, everything has to be periodic in the lattice momentum. So you know eventually you will go back down. And that's the doubling problem. If you start with one single fermion, you actually get one right movers and one left mover in the continuum. And the key insight by Lenny was in the 70s was that if you get a factor of 2 from the doubling problem, you just multiply by a factor of 1/2 in your starting point. And that's why in the original Hamiltonian, you have a single component complex fermion at every side, which is only half of the degrees of freedom of the continuum Dirac fermion. All right, so coming back to here, the idea is that we want to flip the sign of only on this guy, but not that guy. Maybe I got the left and the right backwards. But now it's clear how to do it. Consider the operator TB, which shifts Bj to Bj plus 1. Now, TB acting on a state, B minus K omega. Omega is the vacuum state. Just give you e to the minus 2 pi I K over L times the same state. And in the continuum limit, this phase is roughly plus 1 for states that are close to 0, and roughly minus 1 for states that are close to L over 2. So to conclude, the lattice translation in the continuum limit becomes a chiral symmetry. It flipped the sign of only the, I think somehow I get the left and the right backwards. I'll check that later. But in the convention here, it flips the sign of the left-handed fermion, but keep the sign of the right-handed fermion fixed. Okay. So the upshot is that the lattice operator TB is what goes to this charge conjugation. Continue. But importantly, this TB doesn't act on AJ, so it leaves the AJ fermion in there. Any question at this point? This is probably the most important technical step in the talk.
Hi, I had a question.
Yeah, hi.
So isn't C an anti-unitary operator in the continuum theory?
Which operator, TB?
C.
C, no, it's unitary.
Didn't it take? It's a unitary. It's unitarily realized. It took psi to psi dagger, but it.
Yes, but it takes I to I.
Okay. Okay.
So In fact, if you break it down into Majorana-Weyl fermion, it just flipped the sign of a single Majorana-Weyl.
Okay, yeah, right.
Yeah.
So right, so okay, so it's not an anti-unitary operator. So
Yeah.
then there's no problem. Yeah, so you can realize it
With a lattice
translation. Okay. But this is a kind of this is an exact statement.
Very good.
I
That's a
mean,
very
in the
good
sense
question.
that TB acts on many of the other modes as well, as you said. It's so in
Excellent.
what sense is it?
Excellent.
Yeah, it
Yeah,
goes.
yeah. You see, I was being sloppy in that area. So now, in fact, in my lecture, in my notes here, I wrote the exact equation, but I was being sloppy during the presentation. So let me write the precise relation. The precise relation is that it equals 2 pi I over L PB. Okay, let me go through this exact equality. On the left is a lattice operator. On the right are the continuum operator. CR we have already discussed. What is PB? PB is the momentum operator, the space-time momentum operator for just the B fermion. So on the left, you have the lattice operator. On the right, you have two continuum operators. And the statement that this is an exact equality is on the low line state. So you pick, say, the first 20 states in your lattice Hamiltonian, and you send L to infinity. In that limit, it's meaningful to compare those first 20 states on the lattice with 20 states in the continuum. And you can show that the way this lattice operator acts on these 20 states is in exactly the same way this continuum operator acts on the corresponding 20 continuum states. So this is the precise equality behind.
Okay, thanks.
Yeah. By the way, I should say that this kind of equation was discussed by Meng Chen and Nati Seiberg in 22, and they refer to such symmetry as eminent symmetry. Eminent symmetry. This is to be distinguished from emergent symmetry. So emergent symmetry emerges out of nowhere, but for this kind of charge conjugation symmetry, it comes from an exact lattice operator, but its lattice algebra in the continuum versus in the IR is different.
So on the right-hand side, there is a capital L, but isn't the right-hand side supposed to be a continuum expression?
Very good. So the right-hand side involves two continuum operators, but this L is still there. So yeah, so I probably have to put quotation marks here. But the way to understand this equality is that, as I said, you take 20 states on the lattice, and you send L to be 100 or maybe 200, large but finite. And then you can meaningfully compare this, the action of the left-hand side and the right-hand side.
But I mean, naively, if I just send L to infinity, doesn't that exponential just drop out? Like it's just e to the 0.
That is true. So in the thermodynamic limit, you can ignore this factor.
Yeah.
And that's what I wrote in the first place. But then Rajesh
Okay.
want me to give the more precise version, and that's why I keep it. In fact, let's think about a simpler case. For ordinary lattice translation, it just equals e to the 2 pi IP over L, right? If you have an
ordinary means when it shifts A and B both.
Yeah, no, not even that. You know, consider some, I don't know, some spin model, Ising model.
Okay.
Ising model, the lattice translation just give you e to the 2 pi IP over L. P is H minus.
Yeah.
So this part of the equation is not a surprise. The surprise is that actually there's an internal global symmetry sitting in front of the exponential.
Yeah.
Okay.
And somehow it was also important, the split into A and B is really important, right? That you're only sort of translating the B guys.
Yeah. I think that's I think that's probably the only non-trivial thing about this paper. That you know, if you think about this model in terms of the complex fermions, you wouldn't think about this TB. That's so weird. It acts on the complex fermion in a very complicated way. So somehow the mental block to realize the axial symmetry is that you should break the complex fermion into real fermions.
Yeah.
I think that was somewhat that's the thing that was missing in the literature.
Hmm. In that sense, it's a bit like this Kitaev model, right? Where you see the
I know,
edge mode.
I know, exactly. In fact, I had the identical conversation with Igor.
Hmm.
Igor was making exactly the same point, that this mental block was lifted in Kitaev's paper and also the paper by Kitaev and Witkowski. And we are just playing the same trick, but for different motivation. You're exactly right. But you see, it's actually paradoxical from my point of view. I think for condensed matter physicists and for many people in the lattice community, they love complex fermion and they just refuse to think about real fermions unless they are really forced to. But if you think about it, when we grew up, when we learn math, we first learn real numbers and then we learn complex number. But when we learn lattice fermions, it's the opposite. Okay. So with that, I'm able to deliver the punchline. So we know in the continuum, QA is CR, QV, CR inverse. And now that we have established that CR comes from this TB lattice translation symmetry, we just have to conjugate the easy vector symmetry, the manifest vector symmetry by TB. So let me write QV in terms of the real fermions. So with one line of algebra, you can show that it's just sum over AJ, BJ. And therefore, the axial symmetry is this. All right. And since QV has integer eigenvalues, unitary transformation doesn't change the eigenvalue spectrum. This operator also has eigenvalues, integer eigenvalues. So we have concluded that we have found an exactly conserved integer eigenvalue. Conserved means that QA Hamiltonian vanishes. And let me call it quantized axial charge. By quantized, I mean QA, the eigenvalues are integers. So we have find such a symmetry. And it's a sum of local terms, you see. So you should think about the local terms here as the analog of the time component of the inertia current. So this symmetry is really as healthy as it can possibly be. It's not entirely on-site, but when it acts on a local fermion, it only spread it out to the nearest neighbor. So when we found this symmetry, we asked a lot of people whether this axial charge in the staggered fermion model was known or not. And we couldn't find the right reference. But then in the end, we find two papers that actually mention this charge in one sentence. It's by Thacker from 30 years ago. Horvath, Thacker. They have a very telegraphic and brief mention of this axial charge, and the way they found it was from integrability. But if you look at this the citation of this paper by Thacker from 94 has exactly two citations in the past 30 years. And both citations were from himself. So I think this paper by all definition is entirely forgotten in the literature. But as far as we can tell, it was the first paper who discussed this quantized axial charge on the lattice. But everything I said so far is too good to be true, because I'm saying that there's a vector symmetry that has quantized integer eigenvalues. There's an axial symmetry that has quantized integer eigenvalues. And if it works out in the way just like in the continuum field theory, this will be a violation of the Nielsen-Ninomiya theorem. The statement of the Nielsen-Ninomiya theorem is that you take some global symmetry of your lattice Hamiltonian, you restrict to a fixed charge sector of that with respect to that global symmetry. In that fixed charge sector, you should find equal number of left-handed fermion versus right-handed fermion. Now, if I have QA and QB both on the lattice, I'll be tempted, and they both have integer eigenvalues. So it makes sense for me to restrict to, say, QB equals to +1 and QA equals to +1 charge sector. But in that charge sector, I will have a single chiral fermion, and therefore that would be a violation of the Nielsen-Ninomiya theorem. So something has to give. So it turns out that the thing we have to give up, or the funny property.
Sorry, could you say the contradiction again with the Nielsen-Ninomiya theorem? I just
yeah. So the NN theorem. But this is the version formulated by Denfrieden. Is that on the lattice you have some internal global symmetry G, and G has to satisfy various nice locality property, which are satisfied by our QB and QA. Then in a fixed charge sector of G, we the number of left-handed fermions has to be equal to the number of right-handed fermions. Let me emphasize that it's important to fix usually the way people cite Nielsen-Ninomiya theorem is just that there has to be equal number of left-handed versus right-handed fermions. But that's imprecise. That's imprecise, especially in 3+1D. In 3+1D, if you don't specify any global symmetry, then the left-handed biofermion is the same as a right-handed biofermion. You just take the conjugation, right? In Sriniki, if you take psi alpha, you take the dagger, that becomes psi dagger alpha dot. There's only one vial Lagrangian in 3+1D. But the moment you fix the global symmetry sector, you can no longer take the dagger, and the meaning and the notion of left versus right becomes clear.
Sorry, and in applying it to this current setup, you're using G equals
vector and axial.
So G you take you say if those charges commuted, then your symmetry would be
U1V times U1A, and then I restrict. Yeah, so if they had commuted, I take G to be U1V times U1A.
Yeah.
And then I restrict the charge sector where both of them are +1.
And then you only have one fermion, one left-handed fermion.
Exactly. And that would have been a violation of the Nielsen-Ninomiya theorem. But what saves the day is that they actually don't commute. And now you will ask, if they don't commute, what kind of algebra do they form? So for that purpose, it's convenient to define QB as Q0, Q1 as QA, and then the algebra they form is the following. So let me not give you the definition of all these charges, but this is the algebra generated by QB and QA. So on an infinite lattice, this is an infinite dimensional algebra. Q0 and Q1 are the QB and QA we know. So you take Q0, Q1, you get some G1, and then you take the commutator between G and Q, you get more and more charges. So let me ask, does anyone know what this algebra is? Has anyone seen this algebra before?
In the free fermion, at least in this matrix quantum mechanics setup, people discuss this W algebra. I mean, there is this W1 plus infinity symmetries of the continuum free fermion,
Uh-huh. Oh,
which
I
are sort of
actually,
bilinears, but with higher derivatives.
but does it literally take the same form, or is it
I
just
don't know. I don't know. I'm just saying that
I see.
I'm
Okay.
just like just connecting the dots. I mean, there is this W1 plus infinity symmetry that people who studied, this C=1 matrix quantum mechanics kind of use.
But but I
Mm,
think that one
no,
comes with the
yeah.
gradient, right? That one is probably different.
That's a different Raghu. Yeah, that has two indices.
Oh.
That's like labeled by a mode number and a spin.
Right.
And
Yeah.
you
Oh.
have all the spins from, it's like Virasoro plus all
Yeah.
the higher spin analogs of Virasoro. So
Yeah,
you
this
can, yes. So it has infinitely many more generators.
right.
Okay.
So in the beginning, we didn't recognize what this algebra is, but later on we realized that this is actually the same algebra in Onsager's original paper on Ising model. This is the algebra known as the Onsager algebra. Onsager used this algebra to solve the two-dimensional Ising model. And you can literally find this algebra in his original paper in 44.
These are for the transfer matrices.
Yes, it comes from the transfer matrices.
Okay, and the G's were what in that language?
Yeah.
I mean, the Q's are like the transfer matrices, and
Oh, that I'm not sure exactly, but I can give you the definition for G in our case. So it's sum over J. It's actually much easier to write it in terms of the fermion. So the Onsager algebra is actually not a symmetry of the Ising model, but it is a symmetry of the staggered fermion model.
is it related to the fact that the continuum limit of the Ising model is the 1 + 1 d Dirac?
No, right? Because the Ising model,
at least the real, this equals to half case,
yeah, but this has twice as many degrees of
it
freedom.
has twice as many, but you need them both, right? You're saying that you need both the A's and the B's. It's not just purely with the B's, or
Yes, I need both the A and the B's for this Onsager algebra to be a symmetry.
so Onsager didn't have the A's and the B's as such. He just had the G's and the Q's.
Yeah.
Okay.
Onsager write it in terms of the polys, the poly operators, poly spin operator.
Sorry, I'm a little sorry. If Onsager was solving like the 2D Ising model, right?
Yes.
So he should have gotten the Majorana fermion, not the Dirac
Yes.
fermion.
Yeah.
Yes.
That's
So the
what
algebra in his story is not a symmetry. He
Oh,
only uses it to construct the solution.
I see.
But in our story, it is a symmetry of the staggered fermion. And I should say that this fact, when you bosonize everything, was first noted by Paul Fendley and collaborators. O'Brien, Paul Fendley. There's a third person, which I'm not. There's a paper by O'Brien, Paul Fendley. Let me just get the right. In 2018. But this is they discussed the XX model. So it's the bosonized version of this. So they are locally the same, but globally they are slightly different.
So, and do you have continuum versions of these QNs and GNs?
So yeah, let me discuss the continuum limit. Oops, let me use a new page. So you can show that in the continuum limit, this Qn becomes the vector symmetry if n were even. So I'm picking n to be finite. So continuum limit is taking L to infinity and fixed. And it becomes the axial symmetry when n is odd. And all the GNs goes to 0. So the continuum limit is kind of stupid. The continuum limit trivialized this algebra. And in the continuum limit, of course, QB and QA commute. That's what you want.
Mm-hmm.
So
Well, they commute up to this delta function, right?
no. The delta function appears in the local charge density. This is the global charge.
Oh, the global charge commutes. Okay.
Yeah. Okay, so for people who have slept through the whole talk, let me now give the take-home message. The take-home message is that we study the staggered Fermi and Hamiltonian lattice model, and we find that exactly conserved vector and axial charges on the lattice. But the only price we pay is that the vector and the axial charge, they don't commute. Furthermore, they form the Ansagre algebra. As you take the continuum limit, they become the vector symmetry and the axial symmetry with a Schringer anomaly. So I can summarize the whole talk by this little diagram. And at the level of the slogan, you can say that the Schringer anomaly arises from the Ansagre algebra on the lattice.
Sorry, but I thought the Schwinger anomaly you would somehow need to have, just like you just said, the charge densities, right?
Well,
So we
okay,
didn't discuss on the lattice the charge density.
Very good. So that's what I mean by arises. I don't mean that I literally have the anomaly on the lattice. I don't want to make, because what do we mean by anomaly in this context? It will be an obstruction to gauging that global symmetry. So the way I interpret the anomaly is that the vector and the axial symmetry cannot be gauged simultaneously in the free Dirac Fermi.
Right.
But on the lattice, but before we talk about anomaly, we have to talk about what's the symmetry algebra. On the lattice, symmetry algebra is not even U1V times U1A. It's this whole Ansagre algebra, which is highly non-local. Right? You start with two very local charges, Q0 and Q1. But as you take commutator, it becomes more and more non-local. So I don't even know how to gauge it on the lattice. So I cannot say there's an anomaly on the lattice. The best I can say is that the anomaly arises from some complicated non-abelian algebra. And I think that's one fun thing about this project, that it gives another way for the anomaly of a low energy theory to be matched by the lattice symmetry. Usually, the most naive way for you to match an anomaly between the UV and the IR is that you have the same symmetry group in the UV and in the IR, and they have the same anomaly. Okay, that's the most obvious way to do anomaly matching. But here we have something entirely different. The symmetry algebra are completely different in the UV and the IR, and somehow the anomaly can arise from this complicated algebraic structure. I know I'm out of time, but let me just, can I just take 2 minutes to make one last comment?
Yeah, I think we are also a little bit flexible on time, so don't rush. It's okay.
Okay. Well, I'm almost done. So I talk about this QA, which has quantized eigenvalue. But as you ask, what if we give that up? So in fact, there's another charge, which I'll call Q tilde A. And this was actually already in Lenny's paper, 77. It also commutes with the Hamiltonian. And furthermore, it commutes with the vector charge. But the only price you pay is that it does not have quantized eigenvalues. So if you make a comparison, you can either have a quantized charge or an unquantized charge. This guy has quantized eigenvalues, this guy does not. But This guy does not commute with the vector charge. This does commute with the vector charge. And each of them is compatible with the Nielsen-Denomia theory, but you just have to give something up.
So is the spectrum of Q tilde A known? What is it?
Oh, what is it? Yeah, let me write it.
No, the spectrum. Okay, the charge, but also the.
Let me first give the expression, and I can tell you. Yeah, I can explain more what I meant. That its charge is its eigenvalues is not quantized. So its eigenvalue is like a sine function, some discrete points on the sine function. So there's are generally irrational. So both of these charges in the continuum limit, they becomes the same axial charge. But on the lattice, there are different operators.
So the difference was, if I remember, you only had the first term here in your chart, right?
Yeah, and there's a factor of 2 here.
And the factor of 2, okay.
Yeah.
And I see. So
this is like half of TB QV TB inverse plus TB inverse QV TB. Right? So when we identify TB as C right is an order 2 operator. TB is not. TB is lattice translation. It's Z or ZL. So it's unclear whether we should define our axial charge on the lattice as conjugating by TB or TB inverse, or for that matter, any TB to the odd power. So that's why we have a whole series of operator Qn. All these Qn's are related by TB to the n, QV, TB to the minus n. So the two minimal choices is to conjugate by TB versus TB inverse. This guy is quantized, this guy is quantized, but they don't commute with the vector. But if you take the average, then they do commute with that.
yeah.
Okay. All right. So basically, all I want to say. Let me make a few comments on future direction. So since this is a string theory audience, let me comment that one can do bosonization of this model. Oops, I think I misspelled bosonization. And this will be it will give a lattice model. In fact, this lattice model is known as the XX model. Invented by Heisenberg, which flows to the C equals to 1. So it's not C equals to 1/2, but C equals to 1, because it has twice as many degrees of freedom as the Ising model. It will flow to C equals to 1 with R equals to √2. My convention is that R equals to 1 is the self-dual point. So this is the usually referred to as the Dirac fermion point. C equals to 1 model has a U1 momentum and a U1 winding. Locally, they arise from the U1 vector and the U1 axial symmetry of the Dirac fermion. Now, in the continuum, we know there are these two U1s and there's a mixed anomaly between them. And taking the story here, we can bosonize the vector and the axial symmetry, and that will give us two U1s on the lattice, U1 momentum and U1 winding. But again, the price we pay is that they don't commute. So the bosonization of this story would be to realize both the momentum and the winding U1 symmetries on the lattice. And the lattice model is none other but Heisenberg's XX model. But the price we pay is that the momentum and the winding charge on the lattice don't commute, and they form the Onsager algebra.
Sorry, are you saying that the momentum and winding cannot be simultaneously gauged?
Yes. in the continuum. They cannot be simultaneously gauged.
Hmm.
Yeah, there's a
It's not gauged on the world sheet. We never gauge things on the world sheet, though.
Yeah.
In the string theory context. I mean, of course, there's target space gauge fields that couple to the momentum carrying and binding carrying states, right?
Yeah, yeah. But on the worksheet, you cannot gauge the U1 times U1.
I mean, I guess in string theory, you don't even gauge the individual guys. So,
Well, sometimes if you can, so you know, in the string theory, we gauge the discrete subgroup of that, but that only changed the radius.
okay, yeah.
Okay, so that's one thing we are working on. And the other thing, which we already did in the paper, is that you can actually gauge this quantized axial charge. So our approach gives a new way to gauge a lattice chiral symmetry, and that gives you a different Hamiltonian. And one thing I didn't have time to mention is that we show that for any Hamiltonian that commutes with QB and QA, it has to be gapless. And this is a lattice statement. And it's a very strong constraint that's reminiscent of the constraint from perturbative anomalies in continuum field theory. Usually, if you have a lattice model with a finite dimensional local Hilbert space, the kind of constraint you get is that the model has to be either gapless or gapped, maybe with degenerate ground state. But this is one of the few, this is the only examples, to the best of my knowledge, where the symmetry enforces the low energy phase to be gapless. Okay, yeah, I think that's all I want to say. Yeah, thank you for your attention.
Yeah, thanks, Shu-Heng, for the very nice talk. Can I ask about this gauging this QA? So
Yeah.
I don't know much about this, but this usually when you hear talks, people say that like in the standard model, to put it on the lattice, only the left mover is coupled to the gauge field. And that's impossible to do because you also get the right moving fermion. So is this what you're doing with this gauging this QA? Is that, can you think of it as only sort of gauging the left movers and not the right mover?
Very, very good. The answer is no. So I'm gauging Q axial, and Q axial acts on both the left movers and the right.
Yeah.
Yeah.
Right.
You can ask, well, I cannot gauge Q left because Q left has an anomaly. So I know it cannot be gauged. So in the standard model, what you want to do is that you want to pick a global symmetry that is chiral, but it does not have an anomaly.
Sorry, could you say that one more time?
In the standard model, before you so take the fermion spectrum of the standard model. Right? The thing you would like to gauge is a global symmetry that is chiral, but does not have an anomaly.
Yes.
Right? Such as SU2 weak and U1 hyper. So here you would like to have something similar. You want to take a chiral symmetry that does not have an anomaly. Q axial is like that, but it acts both on the left-handed fermions and the right-handed fermions. And we do not have a realization for Q left, I have to say.
So you can gauge QB, right? Also on the lattice.
Yes, but you cannot gauge QB and QA at the same time. And you can
even
show
on
that
the lattice.
Even on the lattice. You can show that if you gauge QA, QB is broken. And if you gauge QB, QA is broken.
But then somehow you cannot gauge, QB minus QA or something.
So QB minus QA, which you might want to Q left, because QB and QA do not commute, QB minus QA do not have integer eigenvalues. So I cannot couple it to U1 gauge field.
Oh, that is the problem. I see. I see. So this Q left does not have integer spectrum.
Yeah. You can write it down, but it does not have integer spectrum.
Yeah. I mean, you have QB, QA both, right? So you just subtract it.
Yeah.
I see.
So one thing we want to do is the 3450 model. So this is a model of two Dirac fermions, and you assign some U1 charge to be 3 and 4 on the left movers, 5 and 0 on the right movers, so that the anomaly of this U1 cancels, because 3 squared plus 4 squared is 5 squared. That is a chiral symmetry that has no anomaly. And there's a whole community of people trying to gauge it on the lattice.
I see.
Yeah.
So
But I
gauge,
don't
you mean just the left moving charge or something? Gauge the Q left of that guy.
No, gauge that U1. Just that U1. That U1 acts on the left movers and the right movers.
Oh, I see. But separately, yeah, in a different way.
Yeah, in a different. That's right. You cannot gauge a symmetry that only acts on the left movers, because in 1 plus 1D, that's guaranteed to have anomalies. The anomaly is something like sum over the left movers, Q left square, minus sum over the right movers, Q right square. So if you only have the left mover, that definitely has an anomaly that cannot be gauged. Of course, one can still ask, can you realize this anomalous symmetry on the lattice? You just don't want to gauge it. Leave it there. That's an interesting question. That's something we also want to think about.
So you might have mentioned this, but these Q2 and the higher Qs, which are, as you said, conjugation by higher powers of T,
Yes.
So for instance, you could interpret Q2 for also as a axial charge, or it would have a different quantization.
No. So for Qn, when n is even, they go through the vector charge.
Oh, okay. So Q3, for instance.
For Q3, yes.
So, but the charge quantization would be different, the units, or what is different between the I mean, is there anything why you should choose Q1 as opposed to Q3 or Q5 or?
Good. So for all the Qn's, because they are all unitarily equivalent, they have the same spectrum.
Okay.
But then but your question is still valid. Why do I focus on Q1 rather than Q101? The answer is that Q1 is more local than Q100.
Right, it's nearest neighbor.
That's right. Yeah. Of course, if you take the number of lattice size to be 1,000,000, then Q101 is still relatively local.
Sure.
But Q1 is, of course, more local.
Yeah. And okay. And these G's, you wrote down this expression, but you might have said it, but what was the interpretation apart from the Onsager algebra? But in your context, what was the interpretation for the G's?
Yeah, I don't really have an interpretation for G. So G started its life as the commutator between Q and Q. Right. So in the continuum, we expect Q and Q to commute. So G just captures the non-commutativity between them. Now, and G is something that goes to 0 in the continuum. I think that's the reason why I don't have any intuition for them. Furthermore, they do not have integer eigenvalues. So it's not like, I don't think they're associated with an ordinary group-like symmetries. It's just some conserved algebra operator. I wish I have better answers, but that's my current understanding.
Okay. But G1 looks like a fairly natural kind of nearest neighbor operator, for instance, and
yeah, that is true. I mean, it looks like an ordinary operator, but it doesn't seem to be associated with the group symmetry because it doesn't have integer eigenvalues.
Right.
Maybe can I ask this other earlier question, this comment about the W1 plus infinity in reverse? Because the continuum fermion theory is known to have this higher spin symmetries. Does this lattice model have them? It could be possible to write them down, right, in terms of these A's and B's.
Let me think about that for a second.
I guess you could ask about the Virasoro, for instance, to start.
Exactly.
Yeah,
I
like
was,
the stress tensor, right?
yeah. I don't know. I feel like, yeah, I suspect that the integrability people might know this better, right? Sometimes some subset of the Virasoro, such as the KdV charges, probably can be realized on the lattice. I think the KdV charges can be realized on the lattice now that I think about it, right? So what are the KdV charges? They are some combinations of the Virasoros such that they commute with each other.
Mhm.
Right? Virasoros generally don't commute, but you can take some. There are some very sophisticated combinations, polynomials of the LNs such that they mutually commute. And if you have an integrable lattice Hamiltonian, you start with a transfer matrix. You can also get an infinite set of commuting operators. So for Virasoro, you cannot get. I don't think you can get the whole thing on the lattice, but maybe some sub algebra can be obtained from there. And maybe there's something like this in the for this W algebra as well.
I mean, maybe your yeah. I mean, the W algebra usually comes from higher bilinears of the fermion. It's like psi bar psi, but with many derivatives. So, in a sense, the currents that you have are like AJ plus one, or but maybe you can imitate the higher derivatives as well, because you're essentially getting n to the
but basically we do. So this Qn is AJ BJ plus n.
plus n, yes.
Yeah.
So it's some linear combination of, I guess,
yeah.
Higher derivative terms.
Yeah. So
I
I
think
think you could, yeah, you could work directly in momentum space, and I guess make a direct translation there, because in momentum space they are just, yeah, in the continuum they would be just k times psi, k times, let's say in your notation, beta k, beta minus k. That's the usual kind of, but now you would have higher powers of k. So, but in the lattice you had sine pi k, but now maybe you have some assigned to higher powers k.
Right. So indeed, many people brought this up to us, but our Q doesn't. So so let me first make a philosophical comment. So I think the point of this talk is not about finding new symmetries in a free fermion model. Right? Free fermion model is integrable. It has infinitely many conserved charges. So it's not surprising that it has Ansage algebra or whatnot. I feel like what we find interesting about this project is that out of this infinitely many conserved quantities, which people have beaten to death, actually two of them, or actually infinitely many of them, flow through the vector and the axial symmetry in the continuum. Now, coming back to your comment, indeed, in the free fermion model, go into momentum space, you can write out infinitely many conserved operators that take the form of a function of k times beta minus k beta k. However, I think our Q1 does not take that form on a finite lattice. On the infinite lattice, they probably take that form. But on a finite lattice, I think G takes that form, but not Q's. So
maybe, sorry, yeah, go on.
Yeah, so sorry, a related comment is that in momentum space, if you write something that of the form f of k times beta minus k beta k, that looks very natural from the momentum space point of view, but you see it generally acts terribly in position space. And our starting point is that we want to identify charges that act nicely in position space. Our QA acts very nicely in position space. And I think that's the reason that our QA is not of the type that you just mentioned.
So just a related comment is, take the combination Q3 minus Q1 or something.
Right.
And what is its limit as you take the thermodynamic limit? So both of the terms go to the vector charge or something, but is the difference finite in the thermodynamic limit?
I think it goes to zero. in the thermodynamic limit.
Okay, but take some power of 1 over L out or something.
Right. So that will give you something that depends on the momentum. Yeah, I think if you multiply by L, you'll get some non-trivial operator. We didn't really
Right,
look.
so okay, yeah. So you
Yeah,
can or maybe take the limit L goes to infinity, L times Q3 minus Q1 or something.
yeah. That will give you something indeed. We didn't explore that. Yeah, we
And
didn't.
that might have these derivatives, right? Because it'll be A times B minus B
Yeah,
at two different. So
absolutely.
that's like A del B, right?
Yeah.
Anyway, well, that's a side point, as you said. It's not.
Yeah, we didn't try
Okay.
to relate this to the W algebra in the continuum. Yeah.
No, it's not the point, right? As you said, yeah. Okay, I think Rajesh had to leave, so maybe we can stop the recording.
Yeah, sure.